Using the calculator, we can find out that our x component is 107.5 and our y component is 186.12 miles per hour. So in vector form, in component form of the vector, this is going to look like 107.5, comma, 186.12. Now we can continue to look at our second vector that represents the wind and find the components of each one of those vectors, or of that vector. So our x value, we still take the magnitude of that vector, which again was 30 miles per hour, times the cosine of our angle from standard position. So again, it starts from lining up at the x-axis and rotating around. And that was 150 degrees. And then we have our y component, our vertical component, and that's going to be the magnitude times the sine of 150 degrees. We can put these values into the calculator, and notice because I used standard position, it took into account that 150 tells us that this vector is in the second quadrant. Now in the second quadrant, your x values are negative. So when I use 150 in the calculator, I get a value of negative 25.98. If you use the reference angle of, let's say 30 degrees right in here, it would not tell you that this is a negative horizontal component. It's in the negative direction. And then 30 times the sine of 150 is going to be 15. So our components for this vector are negative 25.98 and 15. Now, to find the components of the third vector here, we need to add the components of the first vector with the components of the second vector. Visually, that's what we did right here. We took this red vector and we're adding on the gray vector, the 30 miles per hour. When I add those components together, I get what's called my resultant. So my resultant is found when I add these two vectors together. So 107.5 and 186.12. Add those components to 25.98 and 15. And when I add these components together, oh, sorry, I forgot my negative. When I add these components together, I get a resultant of 81.52 and 201.12. This is the component form of this vector right here in pink. What this is saying is that we would have to go 81.52 miles per hour in the x direction, and we'd have to go 201.12 in the y direction. Let me extend my axis right here. This is 81.52. This is 201.12. These values tell you how much this vector is moving in the horizontal direction and in the vertical direction. But what we want to find is the actual size of that pink vector, of that resultant vector. And how we do that is we calculate the magnitude using Pythagorean theorem. So if I call this vector u, the magnitude of that vector is going to be equal to the square root of the horizontal component squared plus the vertical component squared. Using my calculator, I find out that the magnitude of this vector is 217.013 miles per hour. This represents the airspeed, the actual airspeed of the plane. Now that was only the first part of the question. We were also asked to find the direction angle from standard position. Well, let's revisit what standard position means. if I take my pen and I line it up with the x-axis in the positive direction, and I rotate that to where my pink vector ends, that's the angle I'm looking for. So starting here, rotating it around to where that pink vector is, I'm looking for that angle. Okay, well, there are a couple of ways we can look at this depending on how you drew your picture. And remember, I started this by telling you that this was a right angle. So you could find theta, this little angle in this triangle right here, and then add that on, go back, revisit the first vector. Remember, to the red vector is 60 degrees, so this in here would be 60 degrees. If you revisit that first picture, and then we could add on theta and just use the right triangle. I told you that was a little bit of a shortcut at the beginning of the video. But what I'm going to do right now is look at this as a right triangle. Let me sketch a smaller version with just the resultant down below. Okay, so if I just look at the resultant, remember, we identified that the vertical component was 201.12 and the horizontal component was 81.52. This is a right triangle in here. Using trigonometry, if I want to find this angle in here, and I'm going to call this green angle theta, then I can use tangent to set this up and solve. Remember, the tangent of an angle is equal to the opposite side, so the vertical component, over the adjacent side, which is the horizontal component. To solve for an angle, we have to use the inverse trig function. We have to undo the tangent. And when I put these values into my calculator, I get 67.9 degrees. Now remember, that is from standard position. And that's exactly what the question asks for. It says, what are the direction angle from standard position and the airspeed? A lot of times we're asked to find the bearings also. Well, the bearings would just go from north rotating east, so that would be this angle in here. If we wanted to find that, it's the complement of our angle from standard position. So I would take 90 minus 67.9. So another way to see this same angle would be north 22.1 degrees rotating east. Okay, but for this problem in the specifications, it said find the airspeed, which we did, and find the direction angle. These are our answers for our resultant vector. This is how the plane is actually flying when you factor in the wind.